We're going to start section 3.2 with my catchphrase. And the catchphrase here is that there's nothing new in this video. So section 3.2 is all about talking about something called the fundamental theorem of calculus. Don't spoil it for yourself. Don't look down here yet. And something called anti-differentiation. In chapter 2, we did all this stuff about derivatives. We differentiated functions, found the derivative of functions, and now we're going to anti-differentiate them, which sounds pretty cool. Like matter is cool, but antimatter is even cooler. Derivatives are cool. Anti-derivatives, even more fun. So nothing really new here because in 3.1, we said that the definite integral of a rate of change is just the total change on that interval. Well, that's words. Let's convert those words to math. The definite integral of a rate of change, and what is a derivative if not a rate of change? That's the whole idea of derivatives, right? Derivatives are slope. Derivatives are how things are changing. The slope of the tangent line. So the definite integral of a rate of change is the total change on that interval. The total change is just, well, what's our value at the end? What's our value at the beginning? Find that difference. So the fundamental theorem of calculus, we sneakily introduced it in the last section because it's just this sentence. But now we can write it with math. That's what it looks like in math. So when we're doing integrals, we can essentially do integrals with this idea of undoing the derivative and taking the difference. So let's talk about some language and do a little example, and then we'll do some more examples in the next video. So here's how chapter 2 and chapter 3 are connected. The derivative of a function is f prime. The antiderivative, an antiderivative, that wording choice is very important. An antiderivative of f prime is f. So antiderivative is just flipping, right? 2 squared is 4. The square root of 4 is 2. That's exactly what we're saying here. Like as a metaphor, like squaring and square roots, they're inverses. The antiderivative is basically the inverse. Not theoretically the inverse, but it's basically an inverse of a derivative. So we're just going backwards. That's all chapter 3 is about. So let's do an example. Find the derivative of the following functions. This is easy. Okay, take a moment. Write down what the derivatives of these functions are. Be careful for letter C. All right, hopefully you got that f prime of x for this first one was just 2x. The second one, f prime, yeah, it's still 2x because this is just a constant. And this last one, be a little careful. If it were e to the x, the derivative of e to the x is itself, but e is just a number. That's just 2.71828, blah, blah, blah. The derivative of a constant is 0. So this is also just 2x. So even though there's a letter in there, it's still just a number. That's a sentence you can kind of only say in a math class or physics or some other science. Anyway, all of these functions have the same derivative. There's infinitely many functions that have the same derivative. And if you plotted all of these functions, this first function is the parabola x squared. The second function is the parabola x squared, but it's just shifted up. So notice at any x location, the slopes are the same. The functions are different, which means the y values are different. But the derivatives are the same, which means the slopes are the same. And this is important because of this wording here. if there are infinitely many functions that have the same derivative, that means that each derivative has infinitely many antiderivatives. So, with this in mind, give me 3 antiderivatives of this function. Again, what this means is the derivative of what equals 2x. This inside the blank here is your antiderivative. Okay, that's what antiderivatives are all about. Well, we already answered this. The derivative of x squared is 2x. The derivative of x squared plus 5 is 2x. All of those could go in this blank. The derivative of x squared minus e is 2x. So we just found 3 different antiderivatives of this function. Okay, so 3 different antiderivatives. It could have been x squared, could have been x squared plus 5, could have been x squared plus e. And in general, antiderivatives are just going to be some core piece plus any constant that we want. And we'll introduce that and formalize it in the next video. But this is just a little introduction to antiderivatives. Fundamental theorem of calculus was basically just putting last section into math. The definite integral of a rate of change is the total change on that interval. Let me know if you have any questions, and good luck.